啊！哎，哈哈
反正我妈不会笑，我妈笑都不会，真不行。对。学会他的笑，他那个是很难笑，很难笑出来的。皮笑肉不笑。你那不就是皮笑肉不笑吗？皮笑肉不笑是什么都不知道，真不行。哎，哎，那是嘿嘿嘿嘿，这是皮笑肉不笑。你搞清楚好吧？我两种都会。哎呀，你笑你都不会，你俩开窗了。
哎呀！哎呀！哎呀！盖亚！盖亚！盖！盖亚！这楼爷爷胡子白。乘着乘着 G X X H Z X X X。太离谱了，离谱，离谱！哎呀，真太离谱了！哎呀，真是太离谱了！哎呀呀呀呀！哎呀，这太离谱了！哎呀！啊！哈哈哈哈哈哈！皮笑肉不笑这叫？没，嘿嘿，这皮笑肉不笑。这边身份证、身份证带啊。不让，现在就说。啦啦啦啦啦啦啦啦啦啦啦！这里有水，有水。这装哪儿？
下面过来，我往上面。干嘛？这个东西挂着。你看你那杯不太小吗？就我那个，我那杯。
In this tutorial, I'll introduce you to compute shaders in OpenGL 4.3 or higher and show you how you can use them to accelerate your programs. First of all, what are they used for? Unlike most shaders, compute shaders don't have any defined functionalities and thus they're independent of the graphics pipeline. You can think of them as blocks of code that run on the GPU for just about any purpose you want them to, making use of the parallelism that GPUs provide. But because they are independent and not part of the pipeline, they also don't have any user-defined inputs or outputs. They instead make changes directly on the GPU memory, similar to a void function in C++, which brings us to how they work. Compute shaders can be thought of as a mass of small computers called workgroups. Much like supercomputers, these workgroups are aligned in rows and columns, but also stacked on top of one another, essentially forming a 3D array of them. When creating a compute shader, we can specify the number of workgroups we wish to use. Keep in mind that these workgroups are independent of one another and so shouldn't depend on each other. Then, within these workgroups, we again have multiple threads called invocations. Unlike workgroups, invocations can communicate with one another, as we will see later on in the video. So now let's actually work with a compute shader to get a better idea of how it works. To do that, let's write a very simple ray tracer. As with any shader, we start by creating the shader object, feeding it the source code, and then compiling it. We then need to create a program and attach the compute shader to the program, after which we link it. That's all the setup we need to do. To actually run the compute shader, you need to use GL_use_program and then GL_dispatch_compute, specifying the X, Y, and Z sizes of the chunk of workgroups you want to use. For now, we'll keep it very simple and simply use the resolution of the window for the X and Y sizes and 1 for Z. So basically, we have a 2D chunk. Lastly, since compute shaders are not part of the normal pipeline, other processes might not wait for them to be done before doing something. This is unlikely to happen, but it's still good to use GL memory barrier to prevent this. By plugging in GL all barrier bits, you should be safe, but choosing a specific barrier for your situation might improve performance. Since compute shaders can't render anything, you'll need to make sure you have a texture the size of the window and 2 triangles to render that texture onto using a vertex shader and fragment shader. To render with a compute shader, we'll simply modify the values of the texture. Now for the compute shader source code. As any other shader, it must start with the version you are using. The next thing is the sizes of the workgroups. These are different from the sizes we plugged in beforehand. Before, we specified how many workgroups we want. Now, we're specifying how many invocations we want per workgroup. For now, we'll leave this at 1, 1, 1. We then want to get a texture in as an image 2D. Textures are just one type of data container that can be used with compute shaders. Other examples are uniforms, uniform buffers, and shader storage buffers. Then we simply have the main function where all the magic happens. Remember that we don't have any input UVs like we would in a fragment shader, so we currently don't know to which pixel each invocation corresponds to on the screen. To find out, we can start by getting the ID of our current invocation. How do we do that? Well, I said compute shaders don't have user-defined inputs, but they do have inputs. 5 to be specific. These are GL numWork groups, which contains the sizes of the chunk of workgroups we dispatched. GL workgroup ID, which contains the ID of the current workgroup we are in. GL local invocation ID, which contains the ID of the current invocation we are in, but with respect to the workgroup, not the whole chunk. Then we have two more shorthands derived from the previous inputs, which are GL global invocation ID, giving the ID of the current invocation we are in with respect to the whole chunk, and GL local invocation index, giving the index of the current invocation we are in with respect to the workgroup. The difference between an index and an ID in this case is that IDs contain the X, Y, and Z locations, while an index only has an integer, as if the whole 3D structure was unraveled like a string into a 1D array. In any case, since the workgroup sizes are 1 right now, GL workgroup ID and GL global invocation RD are identical. Try to think why this is so to make sure you understand how things are laid out. We can then get the UVs like so. Notice that I transformed the range from 0, 1 to -1, 1 by multiplying by 2 and subtracting by 1 length of the image size. Now comes the ray tracing part, which I won't explain since that would be a whole video of its own, but basically I'm just creating a quick camera and shooting rays out of all the pixels. If the ray hits the sphere, then I calculate the normal at that point and plug it into the pixel color. That's it for our little ray tracer. Now let's talk a bit more about workgroup sizes. Each GPU manufacturer has an optimization made for a certain size of the workgroups called a warp or wavefront. In my case, since I have an NVIDIA GPU, the warp is 32, while for AMD it's 64. Having multiples of these warps generally improves performance. To make the workgroup size 32, I will make the x-axis 8 and y-axis 4. But we can't run this program yet unless you want to get some weird results. We need to make sure that we are using GL global invocation ID, since now it's different from GL workgroup ID. Try to think why that is so. And most importantly, we now also have to change the number of workgroups we want, since we are now going to have one workgroup for multiple pixels instead of a 1-for-1 relationship like before. So we need to divide the width by 8 and the height by 4 and take their ceiling so that we have the right amount of workgroups for our texture. Now, if we run the program, it should run faster since the GPU is better optimized to work with this warp size. Speaking of which, you can find the limits of all of your sizes by writing the following and running it on the CPU. I'll now introduce you to some more concepts, but sadly, I couldn't think of a way to integrate them into a quick and easy project, so I'll have to give more abstract examples. First, we have shared variables, which are exactly what they sound like. They are variables that are shared by the invocations of a workgroup. To declare one, you must write the shared keyword before a variable, but keep in mind you can't initialize them. In order to initialize them, you will have to make one of the invocations do that, like in this example where I make sure that only the first invocation sets a value for the variable. After the variable is initialized, if you wish to work with it safely in other invocations, then you need to make sure all of your invocations are synchronized. To do that, you can use the memory barrier shared, memory barrier atomic counter, memory barrier image, memory barrier buffer, memory barrier shared, group memory barrier, and barrier functions. All except the last one deal with memory synchronization, while barrier deals with execution synchronization. Keep in mind, you usually need both the memory barrier and the execution barrier. In this example, I have a shared array of size 10, which I first initialize with the corresponding local invocation ID, and then after a synchronization, I add to a part of the array the number to the left. The synchronization is needed here because without it, one of the invocations might be ahead of the others, and so when it would read the number to the left, it wouldn't be initialized yet. Now, here I use a simple plus equals to make an addition. That is because I only have to do one summation for each part of the array. But what if instead of a shared array, we had a shared integer? Let's say we want to sum all the numbers from 0 to 10. The naive thing to do would be to use one of the invocations to initialize the variable, synchronize, and then do a plus equals the local invocation ID. The logic behind this is sound. The problem though is that plus equals, as the name implies, reads the shared variable, adds a number to it, and then writes the variable. But because the invocations are parallel, they would all read the initialized value of 0 instead of a gradual increase from invocation to invocation. This is where atomic operations come in hand. Using atomic operations, we can do some basic manipulations of integers and unsigned integers. So instead of doing plus equals the local invocation ID, we can use atomic add, plugging in the shared variable we want to modify and the number we want to add to it, in our case the local invocation ID. Now this will actually add all the numbers together, unlike our previous method. Now the last thing I wish to cover is group voting. I again couldn't really think of a practical way of showing this, so we'll have to do with an abstract example.